Hello, my name is Ali Reza and I'm the product manager for UGS module in ETAP. Today I'm going to demonstrate the new features that are added in ETAP 26 for UGS module. So here is the ETAP environment, and if you go to cable system group, you can switch to the UGS mode from here. So the very first thing that is added in ETAP 26 is when you want to define a new presentation here. So if you click on this underground raceway system or UGS button here, it's gonna bring you the dialog for creating a presentation. Same as before, you have the option to give it a name here. So let's call it UGS Demo. And then this is a new feature that you have here, which is called methods. So once a new presentation is being created, you have to select the method for that presentation. The first option is Nihir McGrath and IEC. This option belongs to the existing methods that were already supported in ETAP. And the new option is called finite element method. So once you create a new presentation, it will take that method as the property of that presentation, and the study and the features will be based on that presentation. So since this is a new option, I'm gonna move on with this finite element method here. So let's hit OK so that our new presentation is created. So this is the UGS mode now. And as you can see, once a new presentation is created, you have a box here, which is called Cable Arrangement Editor. So this is the new feature that is added to this UGS for this release. Cable Arrangement Editor is a place that once you want to add cables to the presentation, they first go to this Cable Arrangement Editor. So you can select the library, you can define the configuration for that cable, and then move it to the docks or soil. So let's add an AC cable here. Before doing that, let's quickly go over this palette here that we have. We have like docked banks and docks. We have direct bed raceway, which is like a raceway for adding cables. Inside it, we have the backfill, we have AC cables and DC cables. So for now, let's select a new AC cable here. So as you can see, once I click on this one, unlike before, it automatically drops into this cable arrangement editor. And this cable arrangement editor is the place that I can like define how I want to have the cable properties here. So let's double click on the cable to open its editor. The very first option that we need to take is like adding a library to the cable. So we have this library button here, you click on it, and then cable library quick pick appears where you can have like different cables from a set of predefined cables here, or simply you can define a new library here. For now, I'm just gonna pick one of the existing libraries here. Let's say I wanna pick an English cable at 60 hertz, and I want it to be a high voltage cable like this one. And then I can grab the size for the cable, whatever I want. And once the library is selected, this appears on the header of this editor, and I hit OK. So now you can see that I have three-phase cables made of copper, and they are one core cables. So this is where I assign the library to my cable, and then I can put it in any user-defined configuration. For example, I want to put it in trefoil or whatever design I want. So this is so far for the cable. I have selected the cable, and now I can put it or route it into my raceway system. So this is actually the underground or under-seabed system. So it's assume that here is the ground level or seabed level, and this is below that. So whatever is in practice, I can simply implement it here. Let's say we want to put it into a duct bank for the cables. So I drop a duct bank from here and drop it on the raceway system. Then I just open its editor and define its dimension. For example, let's say it's a 50 by 50 inches raceway system, and its depth of burial is like at 15 inches. And here I need to define the resistivity for the fill material of this raceway. Let's assume that it is like 0.8 for if it is concrete, it's generally 0.8 Kelvin meter per watt. So in ETAP you need to make it like Kelvin centimeter per watt. So we multiply by 100, which makes it 80, right? And then I just hit OK. So now I have a raceway here, and it is called raceway 1. So the next step is that I want to put a conduit inside this raceway. So I select the conduit, drop it here, and then double click on the conduit. So here I need to set the distances of the center of this conduit from this top left corner, which works as the reference point for this editor. So let's say it is exactly at the center of the raceway. And then here I can like define whatever is the material for this conduit or duct. We have like metal, fiber, transit, PVC, and again some other options such as fiber and metal again. So the most important part here for the material is regarding the thermal resistivity of that material. Let's assume that we have a PVC duct here, and then I can select its size from a set of predefined sets, or I can give it any values from whatever I have. So let's say the diameter of the PVC duct is like 10 inches and the thickness of the duct is like 0.5 inches. And then the new option that you have here, unlike before, is like what is the conduit fill material or the fill material for this inside the duct. So we have air, water, bentonite clay, sand, and any user-defined material. And for this one, you need to keep in mind that if it is air or water, heat will be transferred inside the duct through heat convection and radiation. But if it is like a solid material such as bentonite clay, sand, or user-defined, which are assumed to be solid, then there is no radiation or convection. It is all about conduction, where heat is transferred through the solid material of the filling. So let's move on with air for now. And thermal resistivity, we have like default values, which are typical values for the air. If you change it to something else, it's going to be updated. But again, you have the option to edit it. It's just a default value, but you have the option to edit it. Now let's hit OK. And you can see that this duct is now applied here. So let's assume that I want to put this cable in this duct as triplex configuration as it is right now. So what I'm gonna do is that I'm gonna select all the cables by keeping Control key on the keyboard, and then drag it inside the duct. And just as you can see, if you move it to the borders, it's not gonna accept it. You can drop it at the bottom of the duct and then just zoom in to adjust the distances if you want to like be very accurate on that. So now I have dropped the cable inside the conduit. I no longer need this one. This is something permanent on this presentation while you're in edit mode. It has no impact on your calculation. It's just like a placeholder for adding the cables. The next step is regarding the soil. So for the soil, you need to enter the ambient for above the ground temperature, or if this is seabed, for the water above the seabed. Let's assume that it is 25, and here are the maximum temperature that is allowed for the cable and the warning temperature. Let's assume that 88 and 90 are the warning and alarm temperature. And for the soil, let's assume that it is like 150 centimeter Kelvin centimeter per watt. Now let's hit OK. And the next step is that I need to enter the loading of the cable here. So I go to the loading page, and let's assume that I want a cable to carry like 300 amps. So I have defined everything here. The physical parameters of the cable generally come from the library. They are crucial and critical for the calculation. So make sure that even if you're grabbing it from the library file, make sure that these parameters are based on the actual values that you have in your cable data sheet. So once I have defined the setting of the study, like soil parameters, raceway parameters, duct parameters, and cable parameters, I'm good to run the calculation. So from edit mode, I switch to cable system tab here. And as you can see, the Niher McGrath and IEC are now grayed out because I'm in a presentation whose type is like finite element method. It's purely based on finite element method. If you're not familiar with how finite element works, it's based on a numerical method which breaks or split this area of the study into very tiny elements, and then it solves the heat transfer equation for set of these tiny elements in parallel and together. So unlike standard methods such as Niher McGrath or IEC 60287, which model the cable system as an equivalent thermal circuit, and they solve it based on some circuit laws. This finite element is purely based on physics law, and this is generally more accurate and more reliable compared to standard methods. So if you open the study case editor from here, you can see that this finite element method has like some options. You need to enter the maximum number of iterations because this finite element method is solved through an iterative process. So you can enter the maximum iteration of this for the solution. the precision of the study, and heat transfer coefficient. So heat transfer coefficient is actually the heat convection factor at the boundary of this ground level between the ground and the ambient air. So unlike uh, standard methods, which assume that there is an isothermal ground level, this finite element method no longer makes that assumption, and it assumes that the the temperature at this boundary is calculated based on the heat transfer coefficient, which is heat exchange between this cable system and the ambient temperature, whose temperature was already entered as 25 for this example. And then we have this report plot details. If you want to see some plots later and you want to have a very accurate calculation, you may want to check this one. If you're not interested in any plots such as heat maps or contour plots, you just care about the calculation, you're good to uncheck it. And this will make the calculation to go faster because it skips some of the necessary parts for the plot. And yeah, so let's move on with these default parameters for now. I hit OK, and then I just hit steady state temperature calculation here. So for the calculation of FEM, as of now, you can only run a steady state calculation. So we hit the calculation and let's give the output report a name. Let's say UGS Demo. Again, for the output report, and hit OK. So this progress bar appears once you run the calculation. And as you can see, once the progress bar is completed, the results appear in this new annotation block that we have added here. So previously, the results were like scattered on the presentation, but now you have a new annotation block which shows the results for these cables inside this raceway. The highest cable is cable conductor cable 1A, which is the top conductor here, and the rest of the cables also the temperature for them is reported here. So as you can see, this interface has been like improved a lot. There are like different options that you can take. If you go to system preferences for underground thermal resistivity, you can change the color for the raceways, for example. If you go here, you can see this color dark band raceway. So you can select from a set of options here. For example, I want to make it like more brownish, maybe. Let's say I change it to this color here and hit OK. And the raceway system is now updated. Also, you can, if you prefer the old annotation, I mean how it used to be before, you can disable this option from the preferences here. So it will like just show the result annotation here. I personally, I prefer to see them in a separate box, so I always enable this one and prefer to see this one here. And yeah, this is for the duct banks. You can have like different ducts here. Let's quickly try something else. So I'm gonna copy this one to the defaults for the duct. Let's say I want to have like simple ducts here, and then I just bring new dots here. I paste it to the default. And let's add one more and one more, and then let's just paste the defaults to these conduits as well. And for this one, let's say I want to have it at 12. For this one, I want to have it at 36, 12. 12, 36, and 36, 36. And now let's say I want to add new cables inside these conduits. Let's just make them somehow different. So for example, for this one, let's say I have a larger conduit maybe. And let's change the fill material for this one to water. So as you can see, once you change it, also the fill material reflects somehow on the presentation. For this one, let's make it to sand. Again, you can see that this one has changed. So let me copy the cable parameters here to the defaults. So I copy data to the defaults. Now, if I add new cables to the system, let's say I add a new cables, it has the properties of the same cable here. Now I'm gonna make this like two parallel circuits. So at the end of the day, I'll have 6 conductors, 2 per phase. So this is 1A, 1B, 1C. Let's drag them here, make them in trefoil. And move them to this conduit here, which is filled with water. And let's move the other circuit for the same cable to this one. Yeah. And let's switch back to previous color, which reflects the color for the concrete as gray. So we have a better understanding of the system. Yeah. Now let's run the calculation again. Why, if the size of the system, number of cables, number of conduits is increased, obviously the computation time will increase because it needs to iterate between more elements. So here again we can see that we have the results for all the cables in this system. So let's take a look at this one and then let's see how plot works here. So if you go to the plot option here, you can see that for the selected output report, you have 3 plot types: cable system configuration, cable system temperature heat map, and cable system temperature contour. So let me select all of them and hit OK, so that the plot is generated for me. And let's see how informative the plot is for this system. So in general, when you grab and select heat map or contour, depending on the size of the network again, the size of the system, plotting may take some time. So the first plot we have here is configuration presentation. This configuration presentation is a very informative plot. It gives you an equivalent plot of what you see on the ETAP site through a plot. So it gives you the ambient temperature here for above the ground or above the seabed. This is your ground level, and this is your soil. So if you hover around it, it's gonna give you the soil resistivity here. And let's zoom in a bit to see what's going on here. So as you can see, if you zoom in, you can see the details of this cable here. We have the conductor layer, which is based on copper. It shows you the OD, the overall diameter of the conductor. Then you can see the insulation layer, its thickness, its OD. Then you have a very tiny and thin sheath layer here. The sheath layer, which is made of, again, copper, it's just 5 mil. The thickness is just 5 mil. And then you have the jacket or serving of the cable. So this plot itself is very informative. If you're interested in like checking the configuration of the cable, this plot helps you a lot to go over it, zoom in, hover around, and see different parameters of your cable. Since these cables are all the same, so the configuration for all of them is the same. But as you can see, again, the fill color for the conduits is different because they are based on different material types. So this is regarding the cables. Now let's check the heat map for this cable system. As you can see, the temperature is displayed for this system that we just modeled in this plot. And I can select and zoom in here and see the results of the temperature all over the presentation through a heat map. So if you hover over the plot, you can see that the Z value here actually shows you the temperature at that certain coordinate that you're hovering. So let me zoom in a bit. And by the way, this is a very dense plot. So depending on the size of the network, it may like take 2 or 3 seconds to like move over it. And as you can see, the hottest cables are the cables on this conduit. They are about like 60 something, yeah, 66, 65, and 65. And for the rest of them, you can also check the temperature. You can click on this button to see the cable IDs on the plot. And beside that heat map, you have the contour plot, which is basically same plot, similar as contour, but it comes with annotations for the temperature. So here it's very interesting. It gives you the exact like temperature contours at different layers of this cable. And you can see how heat flow works inside this conduit and inside this raceway system. So this is very exciting feature. I'm pretty sure that once this product is out, you will enjoy lots of its new capabilities, especially these plot types and this cable system that I have here. Now let's go back to this one and see what else we can do. One of the main things that standard methods are missing is addition of backfill layer on top of the race face. Control backfill layers are generally put on top of the race face using a better material from thermal point of view. So heat exchange can be done better between the cable system and the ambient, especially in cases that soil has very high resistivity. So just let's make it worse. So I'm gonna open this one. Let's assume that we are in a very hot region. We can make it worse. Hot and dry region. And let's run the calculation for this system one more time. Let's wait for the calculation to be completed. So temperature is higher. It may take a bit longer, not necessarily too longer, but just a bit. So as you can see, the condition is now more extreme. So the cable has very high temperature right now. It's like above that allowed temperature, which was 90. So it's turning to red, indicating that this cable is like overheated. Now let's see if we can use backfill to improve heat dissipation for this cable system in this extreme condition. So I'm gonna put this backfill element on top of this raceway and just drag it here. We can also do it from the editor. So let's say I start from 5, width is like 85. It is good. Let's make this 0 and this one 50. So let's say the fill row for this one is like 50. I'm using a very good material for improving the heat exchange between the cable system and the ambient. I hit OK and let's just run it one more time. Okay, you can see that how effective this control backfill is. It helped me to reduce the temperature from 100 to 79. This is pretty good and this is pretty cool. Again, standard methods cannot handle it. So you need this numerical method to model this backfill layer on top of this race-based system. And just to see how it works, if we want to consider it again as the soil as it was, we just need to make this same as soil. So soil has like 300 resistivity. This one is now 300. They are actually the same. So if we run it here, it's gonna give us the same number for the temperature, which was about like 100 something. Let's wait for it to be calculated. And by the way, this is super fast. I mean, regarding the nature of the method, which is like finite element method, which is iterative, this is super quick. And yeah, this is the same. So you can see that how effective is adding like a backfill material on top of the race-based system for this extreme condition. And as the final note, I'm just gonna model the same cable system using direct buried. Let's say you wanna install this one, not inside the duct bank, but uh, inside the soil. So what you need to do is that you grab this direct buried raceway here, drop it, and this is actually it could be soil or it could be different from soil. If this is just like soil, you don't care about its coordinate, right? Because thermal resistivity will be the same. But if it is like a backfill layer itself, then coordinate matters. For this case, I'm just gonna model it as the case that uh, cables are installed in the soil. So all matters for me is just depths of installation. I want to have them installed at depths of 50. So I just grab it here, make it large enough so I can put these cables uh, into this one. Yeah. So let's change the soil resistivity to something else. 150 here. Let's get this one deleted, and let's make this one 150. Okay, and this one is 150. Now it's similar as the soil, but it works as modeling a direct buried raceway system. So what happens here is that you are not allowed to move cables directly from this raceway to this raceway. If you do it, it's gonna throw this message for you. So every time you want to move this cable from this raceway to another raceway, you need to select all of it, move it to the cable arrangement editor, and then bring it back to the to the location, to the new location. So let's say I want to put it at 50 inches here. So I zoom in, I grab it, move it up. You can use these dotted lines here to better move the cable. So I'm here at 50. I can perfectly place them here using these lines. And let's say I want to move the other cable as well. It has two circuits. So I'm just gonna select all of them together, move it. Oops, sorry, I have selected this one as well. Let me put it back to its original position, which was 50. Yeah, I'm good now. Then let's make sure that I haven't selected the other cable. Move them here, zoom in, make them like touching trefoil in perfect position. Same for the other cable. And by the way, it's not necessarily about trefoil configuration. You can have any user-defined configuration for your cables. Unlike the standard methods, which you were forced to put them into like decided positions by the software. In this finite element, you have the full flexibility and full control to do whatever you want with your cables. So let me grab this one, take it here. Let's say I drop it here, and same for the other cable. And now let's delete this one of this arrangement editor here. Yeah, let's make sure that we are putting everything at 50. Yeah. And now let's run the calculation again, this time for this direct buried cable system that we have. So I go to cable system again, run the calculation. So again, we can see that for each of these cables, what is the temperature here. Yeah, and now let's quickly check only maybe one of the plots for this setting as well. Let's look at the contour here. Yeah, when contour plot is being created, you need to be patient a bit, because depending on the size of the system, creating the contour plot may take a while. So while this one is being created, I switch back to ETAP here again, and let's see what else we have here. Yeah, also if you go to the report manager, and from this complete report, if you select UGS FEM, then you have different options for the report, for the format, such as PDF, MS Word, MS Excel. Let's create this PDF format report. And while the report is being created, I can quickly check on the contour plot. As you can see, this contour is really interesting. It gives you a lot of information. So yeah, it shows you the temperature and heat flow somehow inside the system. And now let's check the report here. So you can see lots of details on this report, like the study setting. Let's see the next pages. It gives you the input for all of the cables that you have, such as physical page of the cable. It gives you the raceway systems data, such as direct bait raceway, the size of the direct bait raceway. And here you can see the temperature results for different cables. Every cable in the system it will show the temperature here. And here it gives you the temperature for every layer that cable has. So unlike, again, standard methods, which were only reporting the temperature inside the conductor layer, for this one you can see that whatever layer it has, the temperature is being reported for it. And finally, it shows you the losses in the cable layers that are subject to loss, such as conductor, where Joule losses happen, for insulation layer, where dielectric loss happens, in the cable shield, sheath, and armor, and finally steel duct. If cable is placed in steel duct under certain conditions, some losses may happen on the steel duct because of the current that is induced inside the steel duct. So whatever loss happens in the cable, it will be reported through this comprehensive report. All right. I'm hoping that you are enjoying this new feature. In the next video that I will post, I'm gonna go over benchmark verification for SIGRE technical brochure 880 document. So I will have several sessions to go over different study cases for SIGRE TB880, and we will see that this new engine, which is finite element method, has been verified fully verified against that TB880 with very high accuracy. So I'm definitely sure that you will enjoy these new features because uh, these are something that uh, are very like addressing all the challenges that standard methods couldn't have addressed. And beside that, this new modern interface is super fantastic, and working with this one is super fun. So uh, please share your thoughts and feedback with me, and wait for the next video so we can go over verification process to see how we can model different settings inside ETAP. Thank you for joining this webinar and watching this video, and I hope to talk to you soon later. Thank you.